Going to start looking at the relationships between pressure and temperature and volume in gases. Okay, if you were going to have a balloon and you were going to make it cold, what do you think would happen to it? Would it get bigger or would it shrink? Right, it would shrink, right? So that means you already have knowledge about gas laws, right? That's a basic thing. If you have, let's think about this, a bottle of soda, right? Bottle of soda, you leave it in your car and it's really hot. What happens? Yeah, it could explode, right? But you feel like when you go grab it, isn't it really pressurized, right? All of that stuff has to deal with gas laws and gas relationships about pressure, volume, and temperature. So although they're probably not things you thought about real in depth, you've seen them in real life, okay? You've seen those laws be applied in real life. So anyway, we're going to kind of put some of the information behind that. So we're going to start with what's called kinetic molecular theory. Kinetic molecular theory. Can you break down those words and have an idea about what the concept is? What does kinetic mean? Or kina. Do you know what the prefix kina means?
Something to do with motion.
Very good. Motion. That's it, right? So kinetic is motion, movement. So we're going to talk about how molecules move, right? Kinetic molecular theory. And we're going to talk specifically about how gas molecules move, okay? So there are 5 main postulates we assume for gases, okay? There are 5 main rules or theories that we follow concerning gases. And what we're going to talk about are called ideal gases, okay? So I'm going to even write that in here. 5 postulates for ideal gases. Okay, and when we say ideal gases, it means that we are able to talk about gases that follow the rules, right? And which is a vast majority of them. Talking about gases that are at pretty standard temperature and pressure ranges. If we get into situations in which our temperature and pressure are at extremes, right? Really low temperature, really low pressure, or really high temperature, really high pressure, gases start to behave differently. But ideal gases mean we're in kind of a standard range and everything kind of goes according to plan, right? We're in the, status quo type stuff. So that's really what ideal gases are. If we start talking about real gases, that's when we start to see gas particles that take on what's called colligative properties, and they start to stick together a little more frequently than they're supposed to, and they start to do things that happen in real life but don't follow the picture perfect ideal gas theory, right? So we're going to start with ideal, what we think should happen, and then we might move into a little bit more of real gases. But in ideal gases, they consist of a large number of tiny particles that are far apart. Okay, far apart relative to their size. And so I want you to think about what that means, far apart relative to their size. Okay, can you envision what that might mean? Gas particles are really small, right? Really, really tiny. And they fill the container of whatever they're in, right? But our gas particles are much farther apart than particles in a liquid and much, much farther apart than particles in a solid. Does that make sense? So relative to their size and relative to the other states of matter, gas particles are really, really far apart, which means that most of the time the volume of a gas is really empty space. Right, the gas particles themselves are teeny tiny and they're far apart, and so that most of the gas, right? If I had I'm trying to think of even an enclosed container here. I don't know, somebody's water bottle, right? You've got water in there, but you've also got air, right? Which air is a mixture of nitrogen, oxygen, all those types of stuff, and so it's contained within that water bottle. But most of that is empty space, right? The particles that you have take up that space. But they are far apart. Okay, so that's rule number 1, is that gases are tiny and they're pretty far apart. Okay, so it's pretty simple, right?
What is in that white space?
Nothing. So although we think that air makes up everything around us, that's true. But the actual nitrogen particles, right, the actual oxygen particles are dispersed. Okay, so I'm trying to think about even like a foggy cloud, right? If you see fog outside, you can tangibly see and feel those water particles, right? So they are really densely put together. But if you're talking about just air that we breathe right here, there's a lot of particles in the air, but a lot of that space between them is just purely empty. And when we talk about space between particles, we might be talking about nanometers worth of space, right? It might be an incrementally small amount of space, but those particles are in constant motion. And so the space that's open around us changes all the time. So that's why we're constantly being able to breathe in those particles that we need, because they're constantly moving around in the air. That kind of makes sense or no? Yeah. Okay. It's empty, but the gas particles are so small and for the most part so populated, right? There's a lot of them in the air that you're still going to get what you need out of that. Okay. Yeah. Second assumption we make about ideal gases is that collision between gas particles and between the particles and the container wall are called elastic collisions. So we learned about elastic collisions really in physics, but elastic collisions are collisions in which they collide, right? They hit and then they bounce apart. The opposing type of collision is called an inelastic collision, and that's when they hit and stick together. So what happens in these collisions is that if two gas particles hit, right, they're going to bounce off of each other in what's called an elastic collision, and that's when we don't lose any kinetic energy. Okay, so let's draw out a really basic elastic collision scenario. Have you ever played pool? Right? Okay, the ideal pool ball hit is when you hit the cue ball, it hits the 6 ball or whatever you want to do, and the cue ball comes to stop. Right? That would be a perfectly elastic collision. Whatever energy was contained in the cue ball is transferred 100% to that other one, and this one comes to a complete stop. Is that always what happens? Not necessarily, right? Sometimes the cue ball dribbles a little bit further, right? But a perfectly elastic collision would be a complete transfer of energy. Like you see in those little Newton's cradles that sit on desks, right? The balls swing back and forth and they come to a stop, right? But one ball hits one side and all of that energy is transferred to the one on the other side, comes back, all of it's transferred, right? That's a perfectly elastic collision. And so we want that to happen between gas particles, okay? So a gas particle will move in a straight line until something stops it, right? That's Newton's first law of motion, inertia. Have you heard that before? The law of inertia, an object in motion stays in motion, an object at rest. That's seen perfectly in gases, right? It will continue in a straight line until it runs into something, whether it's another gas particle or whether it's the wall of the container, and then it will bounce, okay? In physics, we talk a lot more about the collisions and the actual dimensions of that. But all right, that's what the next part says. Gas particles are in continuous, rapid, and random motion. They all contain kinetic energy, okay? Do you know what kinetic energy is? Energy of an object that is what? In motion. Yep, good. Kinetic energy is the energy of an object that is in motion. Do you know what stored energy is called?
Potential energy.
Potential energy, good. Potential energy is energy that is stored. It has the potential to do something else, okay? So all gas particles for sure have kinetic. They probably have potential as well. Okay, but that's what we're looking at. Continuous, rapid, and random motion. Okay, this is where we get a little bit sticky. This is when we're talking about ideal gases specifically. There are no forces of attraction between gas particles. Okay, they act like billiard balls. They bounce off each other when they collide. They don't stick together. So ideal gases, that's exactly what happens. They're going to collide and then bounce exactly apart. In real gases, we see a little bit of a hesitation there as the collision comes, right? They want to stick together, but then they'll eventually come back apart. But in an ideal gas, they're going to collide and bounce right back off. Okay? And then the last one is temperature of a gas depends on the average kinetic energy of the particles. So think about this. More energy found in the particles. Do we think higher temperature or lower temperature? Higher, right? More energy is more hot, right? So more temperature, higher temperature. Less energy means our particles don't move as much, right? They're colder. They're going to slow down, right? That connection between energy and the motion of our particles is really, really important. Okay, so that's kind of the understanding we need to have of how gas particles behave as we start looking at gas laws and how they're going to apply. Okay, last thing I want to look at today is pressure conversions. When we talk about pressure, there's like a lot of different ways we can measure pressure for some reason. And so I want to talk about what it means to be at standard pressure and then how we can convert those things, okay? So when we say we have a gas at STP, do you know what STP means? Standard temperature and pressure. It is a set of conditions, okay? Have you learned about STP before? Okay, that's right. Okay, standard temperature and pressure is a set of conditions. So if I say I have a gas at STP, that means I know what the pressure and temperature are. It is a standard set of conditions, okay? So STP is measured in Kelvin. And I'm going to go ahead and put those up here. STP is 273 Kelvin, okay? That means I have a temperature of 273 Kelvin. Do we remember how to convert from Celsius to Kelvin? No, did we talk about that or no?
We never talked about it.
Never yet. Okay, perfect. So if we want to convert from Celsius to Kelvin, we're going to add 273. We're going to take our Celsius temperature and we're going to add 273 to that. So in this case, if I know my standard temperature is 273 Kelvin, that means I'm at 0 degrees Celsius. Right? 0 degrees Celsius equals 273 Kelvin, right? Because if I put a 0 there plus 273, that gives me 273 Kelvin. That's right. 32 degrees Fahrenheit. We're very rarely going to have to convert Celsius to Fahrenheit, right? We would have to maybe go from Fahrenheit to Celsius. We don't use Fahrenheit really. Okay, here's our conversion to get there if we needed to. Okay, if we needed to go from Fahrenheit to Celsius, that's the conversion we would use. Okay, again, not something we're going to do super often, but we are going to have to go from Celsius to Kelvin really often. Okay, so plus 273. So if I had 100 degrees Celsius, how many Kelvin is that? 373 Kelvin. Okay, Kelvin doesn't get a degrees symbol. I don't know why, but it doesn't. Just a capital K. All right, so it's not degrees Kelvin, it's just Kelvin. And Celsius and Kelvin climb at the same rate. So going up 1 degree Celsius means we also go up 1 Kelvin. It's not like Celsius and Fahrenheit, right? The connection between Celsius and Fahrenheit is like, 5 nines, okay? So you've got some weird up and down with Celsius and Fahrenheit, but Kelvin and Celsius climb and fall at the same rate. Okay, units for pressure. There's a lot of different ways we can measure pressure, okay? And so I've got to list them all right here for you. And I don't know if I kept those on your note sheet or not. Did I have you write them in or not? They're kept them on there? Okay, perfect. So pressure is essentially how much force is applied over a certain area. And there are 5 main ways to measure pressure. We want our pressure to be measured in what's called atmospheres. Okay, an atmosphere. So ATM is the abbreviation for atmosphere. That's the unit for atmospheres. And that's the pressure unit that we want to most commonly use. And so that's why I linked every other pressure unit to atmospheres. Okay, it's kind of like moles, right? That's like the one that fits with everything. Okay, so 1 atmosphere is equal to 101.325 kilopascals. That's one pressure unit. Millimeters of mercury is a second pressure unit, torr, and then PSI. PSI is probably one that you've heard before. Where do you normally see PSI in? Tires, right. It says inflate to 32 PSI, inflate to whatever PSI. That means, does anyone know what it stands for?
Pressure per square inch.
No, close. Pounds per square inch. Pounds per square inch. So pounds is the amount of force that needs to be applied over that certain area, square inches, right? So pounds per square inch. That's our conversion there. Okay?
This is measured in weight, basically?
Force is how gravity affects your mass, right? So when it says pounds, that's a way we can measure weight, yeah.
Okay.
All right, so these are all ways you can convert using our pressure units. So we're going to have to do that several times. It's a simple conversion. So if I would give you 836 millimeters of mercury and I wanted it in atmospheres, I would just go millimeters of mercury to atmospheres. 1 is equal to 760, just like that, right? It's a simple conversion, right? The T-chart lives on, right? It'll never die. But it's just a simple conversion like that. Does that kind of make sense? Okay, yeah. Yeah, you might need to go millimeters mercury to PSI, right? And so you would go millimeters mercury to atmospheres to, yeah. So atmospheres is always going to get the 1. Always going to get the, if I wanted to keep going, I would just go 1 atmosphere is equal to 14.7 PSI. Okay, we're going to do an assignment with pressure conversion, so we'll get some practice with that. Okay, the last thing I wanted to point out was that maybe you were familiar with this one, millimeters of mercury. Have you heard that unit for pressure? So millimeters of mercury is how a barometer is measured. Okay, do you know what a barometer is? It measures atmospheric pressure. So let's look at the next slide. I've got a picture here of a barometer. And it says it's used to measure atmospheric pressure. Mercury flows out of the tube until the pressure of the column, right? Until the pressure of the column is equal to the pressure in the dish, right? So mercury will come in and out of that column until it's equal, and then it just measures the height of the column. So when it says millimeters of mercury, we are literally just measuring the height of that column, okay? And so it's measured in millimeters. That would be 76 or 7.6 centimeters, okay? No, 76 centimeters, sorry. All right, so any questions with that? That's just what a barometer looks like, how it's set up. Those are the only two pressure units I think you would be familiar with, millimeters of mercury or PSI. Kilopascal is not, it's not something that we use necessarily in everyday life, but it's kind of the second most common measurement here, okay? So let me give you one more rundown here. When we talk about STP, if I have an object at STP, that means I've got 273 Kelvin and 1 atmosphere. Okay, I like that using these two units. Okay, so 273 Kelvin and 1 atmosphere. Remember, these are equal. Those are equal, so it doesn't really matter which way you slice it here, but we like to use atmospheres and Kelvin. So if we say we have a gas at STP, that means that our pressure is automatically 1 atmosphere and our temperature is automatically 273 Kelvin. Okay.